Good day, students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dongar College, Bikaner. In my enlightening session of MSc Final Physics, I am dealing with the fifth paper, Solid State Physics. We were discussing Wee's theory of ferromagnetism. According to the Wee's theory, a material will become ferromagnetic material for temperature T less than Tc. That means the temperature, this is the Curie temperature, and above this Curie temperature the magnetization is 0 and the material changes to a paramagnetic material. Now in our today's lecture we will derive the paramagnetic region. In this we will study the temperature variation of susceptibility in a paramagnetic region. We know that above the Curie temperature the spontaneous magnetization is 0 and the Brillouin function for smaller values of A is defined as BA equal J plus 1 upon 3J multiplied by A. Here J is the quantum number, and we have already derived that magnetization can be expressed as m equal to n g mu b j j plus 1 a upon 3j. Here g is the Linde factor, mu b being Bohr magneton, and this factor a is expressed as g mu b h plus lambda m multiplied by j upon kbt. Here lambda is the Wee's field constant. Now we can substitute the value of A in this expression and we can solve this to obtain the value of chi, which is expressed as m upon h, and this m upon h can be written in the form C upon T minus Tc. Here C and Tc are constants. These constants are C equal to Ng square mu b square j plus 1 upon 3 kb. This constant C is termed as Curie constant, and this temperature Tc, this is the Curie temperature, and this Curie temperature can be expressed as lambda multiplied by Tc. This is chi equal to C upon T minus Tc. This is known as Curie-Wee's law, and this gives the variation of susceptibility with temperature for paramagnetic materials. It will be evident from the graph of 1 by chi versus T. We are plotting this for ferromagnetic materials, iron, cobalt and nickel. This is the graph for 1 by chi with T. It can be clear that there is a slight difference between these two graphs. This graph, straight line which approaches Tc, and another graph is a straight line which approaches the x-axis towards a temperature T. We can say that the temperature above which the material is paramagnetic, temperature above which the material is paramagnetic and the temperature below which the material are ferromagnetic, there is a slight difference between these two temperatures. T being the temperature at which paramagnetism is set, and Tc is the temperature below which the material is ferromagnetic in nature. we can clearly see that these 2 points do not coincide. There is a slight disagreement between these 2 points. So, experimental data and this Curie law, they only slightly differ. Now, we are moving over to the another topic, an important topic in the magnetism field, that is ferromagnetic carriers. We have shown from the graph of m upon ms versus T by Tc that the ferromagnetism arises because of spin movement, because we have proved from the intersection method that for j equal to half, the curve best fits. That means the magnetization arises because of electron spin. That means Linde factor G equal to 2, and there is no contribution of orbital motion in magnetization. That means we do not have G to be equal to 1. So, for ferromagnetic electrons, the total quantum number J, which is equal to L plus S, as L is 0 since there is no contribution of orbital motion, and S is half, we get J equal to S to be equal to half, and Linde factor will be equal to 2. Confirming that magnetization is largely due to electron spin. And we have also shown in our previous lecture that spontaneous magnetization arises only for temperature range T less than Tc. Tc being the Curie temperature. And for T equal to Tc and T greater than Tc, there is no spontaneous magnetization. Now, since only spin motion is responsible for magnetization, now we will show which electrons are responsible for these ferromagnetic behavior. That means we are going to derive our ferromagnetic carriers. The ferromagnetic substances are iron, cobalt and nickel. The atomic number of iron, cobalt, nickel are 26, 27 and 28 respectively. And from Pauli exclusion principle, we can determine the number of unpaired electron. Since all these elements, they contain argon core. That means number of electrons that are filled are 18. This is the inner inert argon core. So it will have no contribution in magnetization. The outer shells, that means 3D, is responsible for magnetization. Now since in iron, as we can say, 18 electrons are occupied here. Remaining are 8. Out of 8, 2 electrons occupy 4s shell. So we are left with 6 electrons and we are having 3D shell. So 5 electrons set up parallel and 1 left electron set anti-parallel. Similarly in cobalt, which is having 27 electrons, we will have 4s shell which is filled, 4s shell will be filled, and then remaining electrons occupy initially parallel and then they will set anti-parallel. Similar case is shown for nickel. And to determine the magnetization, we know that each unpaired electron contribute a magnetic moment of 1 mu b. And we have determined the number of unpaired electron from Hund rule. The number of unpaired electron in iron is 4, in cobalt is 3 and in nickel is 2. So as each electron contribute 1 mu b, so magnetic moment of iron will be 4 mu b, cobalt 3 mu b and nickel will be 2 mu b. This should be the magnetic moment if we calculate it according to Hund rule from the number of unpaired electron. But the experimental values of magnetic moment completely disagree with this data. The experimental value of iron is 2.22 mu b, cobalt 1.72 mu b, nickel 0.54 mu b. So, it is clear that there is a numerical disagreement between these two data, and this magnetic moment is also in points. That means it have a non-integral value. So our calculation of magnetic moment from the number of unpaired electron is not true in this case, because if we calculate from the number of unpaired electron, it will have an integral value, but here the values are non-integral. So this process of evolution is not right. So for this purpose, we must take into account the band structure. The outermost shells, as we have shown, are 3D and 4s. We are drawing the density of states of iron, cobalt and nickel. Here I am showing this for the nickel. This is the density of state on y-axis, and on x-axis I am plotting energy. We have a narrow 3D band, and this is the 4s band. This is wide and there is a overlapping between 3D and 4s shell. And due to overlapping, in the case of nickel, as we have shown, that there are 28 electrons. Out of this 28, 18 occupy the inner shells which form a argon core. Thus we are left with 10 electrons which will occupy in 3D and 4s shell. Hence in nickel, out of 3D, 9.4 electrons are distributed in 3D shell, and remaining 0.6 electrons from 10, they are in 4s band, and occupation takes place according to Hund rule. So out of 9.4 electron, 5 electrons initially set their spin parallel. We are left with 4.4 electrons, and these 4.4 electrons will set anti-parallel in 3D shell. Hence, the net spin will be 5 minus 4.4, which is 0.6. So, we will be having a magnetic moment of 0.6 mu b for nickel. We have shown that experimental data for nickel is 0.54 mu b. These two values are in fair agreement to each other. Hence, we can determine the magnetic moment not simply from the unpaired electron, but for ferromagnetic materials, it will be determined by taking the overlapping of 3D and 4s shell, and then it will be determined according to the Hund rule. The remaining unpaired electrons, they will give us a magnetic moment. Now, this is the magnetic moment for nickel. If we alloy nickel with zinc or copper then a change in magnetic moment will appear. If we add copper to nickel, then addition of a copper to nickel introduces one extra electron. Whereas when we add zinc, two additional electrons are introduced in the crystal. And these additional electrons, whether it is copper, whether it is zinc, they tend to fill the 3D shell. If the 3D shell completely fills, then there will be no unpaired electrons, hence magnetization will decrease. It will result in a decrease in the magnetic moment. And it is clear from experiments that when we add 60% copper to nickel or by the addition of 30% zinc to nickel, the magnetization becomes zero. So, we can conclude that in iron, cobalt or nickel, the magnetic moment will be determined not simply by number of unpaired electron. That means we can conclude that the magnetic moment can be determined from the overlapping of 3D and 4S shell, and the non-integral value is also justified by using the overlapping of 3D and 4S shell. So, from Weis field theory, we can arrive at three most important conclusions. The first is that magnetization arises only when temperature is less than Tc. That means spontaneous magnetization has an existence below the Curie temperature. The second important conclusion that we have drawn is that magnetization which arises for temperature less than Tc, this magnetization arises only because of spin movements, because we have proved that J equal to half and orbital motion has no contribution is in magnetization. The third important conclusion is for ferromagnetic carriers. Ferromagnetic carriers are the electrons which are obtained by the overlapping of 3D and 4S shell, not simply by determining the number of unpaired electrons using Hund rule. Thank you students for watching.